Hi, everyone. In this recording, I will present the 2019 article titled The CAPM Strikes Back and the Equilibrium Model with Disasters, published at Journal of Financial Economics. This is a joint paper with Han Bai, Kowei Ho, Howard Kuhn, and Erica Lee. In this article, we show embedding disasters into a general equilibrium model with heterogeneous firms induces strong nonlinearity in the pricing kernel, thereby helping explain the failure of the CAPM and the consumption CAPM. In other words, in terms of methodology, we extend the Zhang 2005 model to general equilibrium. In addition, in terms of substance, we embed disasters into the model, and doing so makes the model more nonlinear, and this nonlinearity helps the model explain the stylus fact that the CAPM and the consumption CAPM both fail to explain the value premium. So a bit more specifically, our single factor model embedded with the disaster shocks tagged on, our single factor model in which a nonlinear consumption CAPM holds exactly by construction quantitatively replicates the following stylus facts. So we show that the unconditional CAPM fails to explain the value premium in finite samples without disasters, but succeeds in samples with disasters. So the economic intuition or mechanism is that without disasters in a finite sample, the estimated unconditional betas only reflect risk in normal times without capturing any disaster risks. However, the value premium is driven by disaster risk because you cannot detect disaster risk in your estimation based on no disaster samples, and therefore the CAPM fails. So the model also managed to explain the beta anomaly, which is a flat relation between pre-ranking betas, market betas, and the average return. It turns out intuitively, in the model, the pre-ranking beta comes with large measurement errors. The pre-ranking beta and the true beta are oftentimes only weakly correlated, and the correlation is often even negative. So measurement errors are the source of the beta anomaly, are the source of our model's explanation for the beta anomaly. And finally, we also explain the failure of the consumption CAPM. So in particular, the standard is the canonical power utility-based linearized consumption CAPM fails to explain the 25 size and book to market portfolios. It turns out in the model, the contemporaneous consumption growth has virtually nothing to do with the pricing kernel, because the pricing kernel is very nonlinear, and with the recursive utility, the continuation utility term has very strong nonlinearity due to disasters, whereas the standard linearized consumption CAPM based on contemporaneous consumption growth has virtually nothing to do with the true pricing kernel. And we will present the detailed results later on. So why is the contribution important in our view? Well, so early investment-based asset pricing theories mostly rely on single factor models. So in which the CAPM roughly holds. In a prior video presentation, I presented the Zhang 2005 article in which the model fails to explain the failure of the CAPM in explaining the value premium. In other words, in that model, the unconditional CAPM roughly holds. The conditional CAPM holds exactly, and unconditional CAPM performs pretty well, and because of the single factor model. So the bottom line is that the nonlinearity in that model is not that strong. The model is nonlinear, but it turns out the linear CAPM approximation, linear CAPM-based pricing kernel still performs pretty well. in the simulated data. The more recent theoretical models introduce multiple shocks. However, these models are inconsistent with the long sample evidence, in which we will show just in a little bit that it turns out in the long sample, including the Great Depression, started, in the long sample that starts from July 1926, that sample includes the Great Depression. It turns out the CAPM, unconditional CAPM, does pretty well for the value premium. So, and the prominent examples including Ayakiku, Kogan Papanikolaou, Bellow, Ling, and Bastchurch. So all three articles, along with several others cited in our paper, so they have multiple shocks. So in Ayakiku, that's long-term and short-term productivity shocks, and investment-specific shocks and TFP shocks in this paper, and TFP shocks, total factor productivity shocks, and adjustment cost shocks in this paper. So although they explain the failure of the CAPM because of multiple shocks. However, the multiple shock models cannot explain the long sample evidence in which CAPM actually works for the value premium, because they will always fail the CAPM. So the paper is also related, is also related to disaster models, and Reed-Sparrow and the Francois, very nice AER paper 2012. So, but all these models are about aggregate asset pricing only. They were looking at the equity premium, and we integrate this exhaustive disaster literature with the investment-based asset pricing literature, and trying to explain we're building on the disaster mechanism in order to resolve a long-standing puzzle in the investment literature to explain the failure of the CAPM. That's the big picture of the paper. All right, so the outline for the presentation, I will first present the stylized facts that we set out to explain. So quite a bit of stylized facts. In fact, I'm going to describe the model. Now the model is quite full-fledged, I would say, although conceptually remains simple, but lots of bells and whistles. So then I'm going to describe the calibration and the basic moments from the model, describe the equilibrium properties of the key moments like risk and risk premiums and how they vary with Berkshire market. And then I'm going to explain the failure of the CAPM in the model and the failure of the consumption CAPM in the model. And finally, before I conclude, I will only summarize without reporting the details the key comparative statics results. All right, stylized facts. So quite a few stylized facts. The first table is 10 booked market deciles, average access returns, and the CAPM statistics, alpha, beta, and t values and all in the post-CompuStat sample from July 1963 to June 2017. So, and the data source is Ken French's data library. So, booked market, the sample ends in June 2017. So I just recorded the value premium paper presentation. I talked a little bit, extended the sample to December 2020. You should check out that presentation as well. So if we end the sample as we did at the time, that's all the data we had when writing this paper. So in June 2017, if we end the sample there, we still have quite a reliable value premium, 47 basis points per month, t-value 2.5. CAPM doesn't do much, although beta is weakly positive, is insignificant, and alpha is 43 basis points, only 4 basis points reduced from the average return. Although we're already starting to see signs that that in this case the value premium is actually the CAPM alpha for the value premium is starting to show marginal insignificance. 1.9, it's on the boundary. But the bottom line is that, let me focus. The beta is really small. CAPM still doesn't do much in the overall. CAPM doesn't do much in the post-compute stat sample. On the other hand, this is a evidence emphasized by Andrew N. and Joe Chen in their 2007 Journal of Empirical Finance paper. So if you looked at Ken French's data going back to July 1926, so value premium remains roughly on average unchanged. But now look at the alpha and beta. Beta in contrast, only in 0.007 in the modern sample. In the long horizon, in the long sample is 0.45, t-value 3.9. Now alpha is only 19 basis points and t-value below 1. So in other words, in the long sample, the unconditional CAPM actually captures the value premium. And if you look at the pre-compute stat sample, again using Ken French's data set, 1926 to 1963, the value premium on average hardly changes, remains at 51 basis, actually slightly higher, 51 basis points per month, although shorter sample t-value is not significant. But look at the let's just focus on economic magnitude. Economic magnitude of beta is 0.71, highly significant, 5.3 t-value. Alpha is now negative, although insignificant. So bottom line is that, so we interpret this evidence as saying the Great Depression really has a big deal, has a big impact on the performance of the value premium and its CAPM performance. And then I started to think, hey, so back in 2005, in my value premium paper, and the causal mechanism is that value is riskier than growth in bad times, and Great Depression was like the baddest of all times, right? The worst times ever. So it's maybe we should extend the model into disasters, and that's the step we took in this paper. So scatter plots. This is the left panel is the long panel, long sample. The right panel is after 63. The scatter points dated and highlighted in red. These are the 3% extreme observations of market factor returns, of market access returns. It turns out they are all in the long sample, they're all in the pre-compute stat sample. So, and they are all extreme. So bottom line is that if you fit the complete observations, including this large swings in the market, it turns out that if you fit the value premium on run a linear regression of value premium on market access returns, you see evidence of risk in the long sample. Whereas in the post-compute stat sample, that line is pretty flat, okay? So a little bit closer look into the large swings in the stock market. So again, 3% extreme observations. So it turns out whenever market jumps a rebound, okay, let's look at the downside first. Whenever market drops big time, the value premium drops big time as well. However, whenever market rebounds, huge market access returns, value premium does pretty well also. Okay, and we also know some of these states are exactly when momentum crashes, as highlighted in influential work by Toby and Ken Daniel and Toby Moskowitz. So there may be a paper to be written later on. Maybe this model has something to say about the momentum crashes, and that's on our radar as well. All right, so let's take a closer look at these extreme observations, large swings in the stock market. So when the market, for example, in August 1932, when the market jumps 37% in that month, high minus low this is the High-Manor-Slow decile, hits the highest in sample, 68% for that month. On the other hand, the lowest market drop is in March 1938. The market drops about the 23.8% for that month. HML drops by about slightly over 20%. More recently, right after Lehman, so in bankruptcy in October 2008, the market drops by a little bit over 17% in that month. High-Manor-Slow drops by close to 10, almost 10%. So bottom line is that, and if you calculate the correlation between market and High-Manor-Slow using these observations, you get a correlation as high as 70%. So bottom line is that looks like there's some strong evidence for risk behind the value premium. All right, now let's look at the beta anomaly. And the evidence of risk for value premium is bigger risk. We're talking about the Great Depression, economic disaster. Whereas if you look at just the post-Compuset data, the risk evidence is fairly weak. Right? All right, let's look at the second anomaly we are looking at, which is the beta anomaly. So this is Frazzini and Peterson the beta anomaly dates back to Farmer Macbeth, actually. So if you sort stocks based on pre-ranking market betas, these are rolling 6-month rolling window. The sample is the post-Compuset after 1963. You see High-Manor-Slow, there's nothing going on. Sorting on beta doesn't generate average return spread. It's only 3 basis points. However, pre-ranking betas give rise to post-ranking beta spread. Okay, so the High-Manor-Slow pre-ranking beta leads to like a post-ranking beta of 1. Okay, highly significant. As a result, CAPM alpha is strongly negative, almost significant. This is pretty significant. Although slightly below 2 or 1.96 for that matter. Look at the economic magnitude, 52 basis points per month with a negative sign. Because in the CAPM, the average return spread is close to 0 and all this beta risk has to go somewhere. It shows up in alpha. In the long sample, and from 2026, we require 24, minimum 24 month in the rolling window. So it's from July 28. Starting from that point for the pre-ranking beta portfolios, so the results are quite similar. So High-Manor-Slow, it's very small average return spread, and pre-ranking beta leads up, gives rise to a big post-ranking beta spread, and that beta risk has to go somewhere. That goes into alpha. As a result, the alpha is significant, large, and negative, and the significant 2.8 p-value. So the final aspect of status facts is consumption CAPM. We are looking at 25 size and booked market portfolios. Annual data on this slide dated back to 1930. So this is 25. So size and booked market portfolios as in Pharma French 1996. So you see value premium is stronger in small stocks, High-Manor-Slow among small stocks. So we're looking at more than 12% per annum. And whereas in big stock is only a little bit over 4%. However, such average return spread doesn't show up in consumption betas. And consumption beta is based on first stage regression, time series regression of annual return portfolio returns on contemporaneous consumption growth. And consumption is measured in the standard way and non-doables plus services. So despite high small stock value minus growth premium, consumption beta actually goes the wrong way. Small value portfolio has a lower consumption beta than small growth. And similarly for big stock value versus big stock growth. The evidence is similar for post-war quarterly data. This is from 2047, the consumption data, of course, from NIPA. Again, in the quarterly data, small stock value premium is the highest, higher than big stock value premium. However, consumption beta continues to go the wrong way. Small stock value portfolio has a lower consumption beta than small stock growth portfolio. If you do the second stage cross-sectional regression to test the consumption CAPM, and this table will be the result. First of all, the model is rejected by the chi-square test. The chi-square test is testing the intercept plus residuals being zero, being jointly being zero. So if you look at the intercept per se is significant, phi 0, and the phi 1 is the price of consumption risk, is insignificant, although positive. That's good. Quarterly data post-war sample is similar. So long sample doesn't make it much of a difference. So in terms of scatter plot, this is a predicted premium out of consumption CAPM against realized returns. You see that the scatter plot is basically a horizontal cloud. The consumption CAPM, the standard consumption CAPM based on consumption, contemporaneous consumption growth has very little explanatory power for this testing portfolios. This small growth, this small value, small growth, small value, with or without disasters, doesn't make much of a difference. So those are the status facts that we set out to explain. Now let's look at the model. So a bird's eye view, we embed the economic disasters into a general equilibrium production economy. So real disasters are exogenous disasters in productivity growth and basically are following Rees and Barrow in spirit. Rees and Barrow both work with the consumption model. Endowment economy, we work with production economy, as in Francois' 2012 AER paper. So we combine that also with heterogeneous firms, cross-sectional distribution, endogenous, with asymmetric adjustment costs or cost reversibility, as in my thesis. And we're going to close the model this time after 14 years, 14 years. So, and in this paper, and we're going to take the step to do general equilibrium, and we're going to overcome the computational burden of proximate aggregation using Croissant-Smith algorithm. So the basic mechanism is basically value stocks are more exposed to disaster risk than growth stocks. So in my thesis, I was saying because of costly reversibility and the counter-cyclical price of risk, value is riskier than growth in bad times. Now we have disasters. Value stocks are really riskier than growth stocks in disasters. All right, so that's the bird's eye view. Now let's feed in the details, bells and whistles, lots of them. Recursive utility, absenzing utility, pretty well known, and that's the pricing kernel. So on the production side, we have a decreasing return to scale, and we're going to model aggregate shock in terms of growth rates. Okay, so firm-specific shock in terms of the level, So the growth rates are not very persistent, so at all. So we work So we just work with this discrete state space with only 5 state variables. Okay, so we use a Rowan-Horst procedure, only 5 states, and that's more than sufficient because persistence is not very high. So, but we're gonna model, yeah, the persistence for the normal states is not a very normal time. Normal states is not a very high. So we're gonna model this. We're gonna model disaster on the Markov chain directly following a cool paper by Dante and Donaldson. So 1999, very nice paper, only published, seems to be underplaced in economic journal. I guess at the time, the Reed's disaster model was still pretty much on the back burner on everybody's minds. So, so insert the, we're gonna borrow a modeling technique from Dante and Donaldson. So we're gonna insert a G0 as a disaster state and the G6 as a recovery state. We're gonna modify the transition matrix by adding theta as the persistence for the disaster state and eta as the disaster probability. Basically, the economy can fall into economic disaster with the probability of eta starting from any of the 5 normal states. Once in an economic disaster, with the probability theta, the economy is going to stay in disaster. With the 1 minus theta probability, the economy is going to enter recovery state, okay? So it's going to persistent with new probability, and after that, it enter any one of the 5 normal states with equal probability, and you cannot enter a double-dipped economic depression disaster. So, but we haven't tried. We didn't try, but we don't think you know, adding some probability there will make a whole lot of difference. So capital accumulation, fairly standard asymmetric adjustment costs with a little bit of linear cost there as well, and the quadratic adjustment costs as usual. So we're gonna keep costly reversibility in the sense that firms face higher costs in cutting capital than expanding capital. The firm's problem, so we're gonna have cross-sectional distribution now. This is really important because we're doing general equilibrium, and the investors have to forecast future consumption and in order to calculate the pricing kernel. Okay, so mu is the distribution including firm-specific capital and firm-specific productivity. So value maximization, investment policy, we also include exit policy. So S is a parameter that controls the liquidation value. In our benchmark calibration, this is basically 0, but we experiment with alternative values in comparative statics. So if it's 0, but bottom line is that if the value is below 0, shareholders is gonna exit. It's gonna take a 0 and walk away. And that's exit, and we assume firms are gonna take the delisting return. For that exiting month, it's going to enter an immediate reorganizational process and take the fraction kappa. So it turns out it's to be quantitatively not that important. So take a certain fraction, like let's say 10% of the capital stock, and the remaining capital stock, 1 minus S minus kappa. So it's going to form a new firm. Okay, and new shareholders gonna come in and take and start to operate the new firm. So we're gonna assume the reorganization process happens immediately to keep the computation tractable. So the number of firms remain constant in the cross section, but with some immediate reorganization whenever a firm needs to exit. So starting from this value function, and assume for incumbent firms that do not exit, you're gonna have, and for exiting firms, you just get the listing returns, minus 12.3 on average in the CRISP data set. For the incumbent firms that do not exist, you can calculate the returns. So basically cum dividend firm value next period divided by cum dividend value today minus dividend today. All right, and that return is gonna satisfy the fundamental equation of asset pricing, also holds in the production economy. All right, and then you can use the definition of covariance and write it out as risk premium equals true beta times price of beta, price of risk. Okay, so and the true beta is defined vis-a-vis the pricing kernel, and the phi is the price of risk and given by this term, and beta is given by this term. It's conditional, it's time varying. Okay, and you can estimate the unconditional version of it by regressing returns on the pricing kernel contemporaneously. Recursive competitive equilibrium, the model is a bit involved, bells and whistles, and I should explain. We felt like we should model exit decision because we have disasters, and ex ante we were worried that lots of firms are not going to survive disasters, so that's why we put it in. Recursive competitive equilibrium consists of optimal investment rule, exit rule, and the value function, equilibrium law of motion for the firm distribution such that the optimal policy and the value function solve the firm's problem. Consistency says that the aggregate behavior of the economy, not just the industry, in my thesis, the aggregate behavior of the economy is consistent with all firms in the economy. That means output, okay, investment, capital, and adjustment costs all gonna add up. All the aggregate variables have to, it just are the outcome of the individual variables adding up. So this is the literal micro foundation. Consistency continues. That means that the law of motion for the firm distribution has to be consistent with the individual firm's decision. Okay, and that's given right here. I mean, theta is measurable set again, so gotta be fun. So one of my advisors in grad school, so when I was writing this down in my thesis, he was joking with me, were you on drugs? So when you write down measurable set, so it was like, hey, I was working with the Croissant Smith. I don't need drugs to get high. So working with Croissant Smith, approximate aggregation is getting high enough. All right, so this jokes aside, so although the equations look pretty technical, again, intuitively is actually quite straightforward. So all this is saying is that the next period distribution is current period distribution bundled with the current period firm decisions. That's all that is saying. This is all that is saying. Okay. Looks intimidating, but well, the computation is intimidating. But that's why it took 14 years for us to complete this extension, because I was literally resisting. No, I don't want to go. No, I don't want to go there. Then a referee said, please go there. So we were like, okay. But we're pretty happy we made the step because we get to have something to say about the failure of the consumption CAPM, and without the G extension, that's not going to work. We will have nothing to say about the consumption CAPM. So we are happy we made this step. Took some work, but it's worthwhile. All right, market clearing condition. So aggregate consumption equals aggregate output minus investment. This means consumption equals dividends plus a bunch of costs. So we throw fixed costs of production and the capital adjustment costs. We interpret this cost as compensation to labor, which is not explicitly modeled. Labor is not the independent input, productive input. And we interpret this cost as compensation to labor, therefore part of consumption, because this helps explain the risk premium, the magnitude, because this drives a wedge between consumption and the dividend. So Andy was using, in his 1999 GME article, using consumption leverage in a production economy. So the consumption leverage is actually endogenous, and that's our way of going there. So more bells and whistles, because we're modeling aggregate shock as shocks on productivity growth. So the model has growth, and that means we need to detrend. And we detrend all the variables using elected value of xt minus 1. And so this is the detrended value function, very similar to the undetrended. So the only difference is that you need to carry this term around, which is the growth rate of aggregate productivity. All right, and lots of other variables. The equations are in the paper, and the part that is that took a long while. A big shout out to Erica, and she's the one who solved the model. Without her, this paper will not be feasible. So we implement the Croissant-Smith in a model with disasters. Ex-ante, it was not clear to us at all whether we could solve the model, because Croissant-Smith, the original article, the model is not that nonlinear. Okay, there was certainly no disaster. The equity premium, risk premium is practically zero. So the log linear model will fit, right? So 99999 after the decimal. But in our model, we have a disaster. So ex-ante, we were worried about that. So it turns out the way to deal with it, it turns out it's still okay. It's still feasible. The way to deal with is to specify a log linear law of motion. Well, not exactly linear, we put the quadratic term. Well, log linear in terms of it's like you're running a regression. This is a linear regression. So the log linear, mostly log linear law of motion will still work as long as you allow the coefficients to depend on, to conditional on the aggregate state variable. So instead of just simulate the economy and then fit the one law of motion, we fit the multiple laws of motions. Laws of motion, each of which correspond to a given value on the aggregate grid, including the disaster grid point, disaster state. And that nailed it, okay? We were pretty happy to see that. Right, this J stands for different iteration, and this I subscript stands for the index on the grid, aggregate grid, aggregate state productivity shock. So we need to solve for the K bar is the aggregate, the detrended capital. And the C hat is the aggregate detrended consumption. So basically we are assuming, so K bar is the only state variable, aggregate state dependent though, that captures the whole cross-sectional distribution. And the final outcome is pretty reasonable. So for the k-bar state variable, we have like a whole bunch of nines behind the decimal. For consumption, it's a little bit less accurate, but we still judge it to be reasonable. The R square is 0.99495. So it's fairly comparable to some of the prior literature, prior studies that also used Croissant-Smith on consumption. So it took a while, and basically, because this step, the outer loop, as usual in the Croissant-Smith algorithm, is not contraction mapping. The inner loop, value function iteration, is contraction mapping. It always converges, but not the outer loop. So, and in practice, we only managed to shrink the errors to 10 to the minus 2, but we feel comfortable. We should say we feel better. We feel comfortable that the R square for detrended consumption is 0.495, which is fairly reasonable. And we only managed to achieve that by simulating a huge number of firms. So in our simulation, we only used 5,000 for producing moments, but in solving the economy, a competitive equilibrium, we implemented 30,000. This is through extensive trial and error, only through 30,000, and the model, first of all, will converge, and second of all, achieve high levels of R square. So this is, hard work. All right, now let's look at the basic moments. So first, I should talk about the calibration first. So time discount factor, risk aversion, EIS, intertemporal elasticity of substitution. So this rho G is the persistence in normal times, and that parameter is not important at all. You can put it virtually IID, results won't change. And we have experimented that. Disaster probability, we're using 2%. It turns out that's not the important parameter. Yeah, maybe I'll keep that to later when I talk about comparative statics. What is important is the disaster size, disaster persistence, okay? This is the recovery size, recovery persistence, and we calibrate the disaster parameters such that the impulse response of consumption to a disaster shock looks like what we observe in the data in the Barron-Uswa cross-country panel. So in Barrow and also and co-authors AEJ macro. So they documented the impulse response for consumption. So their short-term, well, it turns out our disaster calibration is more conservative in the sense that our mean and the median short-run impact is about 14%. Upon impact on disaster, in the short-run consumption will fall by about 14%. In the long term, stays about 9%. The median is a bit further away, so 19% and 12% the long term, 19% in the short term. So in the AEJ macro, so the short-term impact is actually quite a bit bigger. It's like 28, 29. And the long term is about 14% long-term impact. So we are in the range. We are more conservative. But that's the left panel. In the right panel, we are plotting some standard errors out of the model simulation is quite wide because we're looking at disasters. So this moment's impulse response come with the large standard errors as probably should. So this is this is not 95% confidence interval. This I think only 68%. 95% is even wider, right? So that's what these parameter values have achieved. So in particular, the disaster side, disaster persistence are fairly consistent with the prior literature, in particular, Gorriel's 2012 AER paper. So I should mention that the recovery size and persistence are a bit like three parameters, okay? They help us to match the impulse response, but they are not very important for our key moments later on, because they're about good times that investors don't really care. What investors really care about is the disaster parameters, not the recovery parameters. So I will have more to say about this later on in comparative statics. So this is decreasing return to scale, curvature in the production function, 0.65. Delta is monthly depreciation rate. F is fixed cost of production. Z bar is a long-term mean of the firm's specific productivity, right. So the rho and the sigma Z a little bit higher because you need to take the Kc power a little bit higher than whatever I was using in my thesis, but they're important for generating enough dispersion in the cross section, and the rest are the adjustment cost, A bar, A plus A minus, C plus C minus. So the liquidation value, we're putting it to be 0. Shareholders get nothing in bankruptcy or in exit. Kappa, this the reorganization cost is 25%. It's not 10% I was talking about before. The listing return, I remember that one, minus 12.3%. So the key moments, nothing unusual. So volatility in the data is about 4.9. This is output 4.9. We have 4.4. Persistence in the data, this is the US data only. Annual and quarterly. Consumption, so in the model, we're a little bit higher now. Okay, but that volatility is actually quite consistent with the international panel, especially in the long historical panel, long historical cross-country panel with disasters. Investment growth, we're a little bit more volatile than that in the data, but less volatile in the quarterly data without disasters, post-war quarterly data. Now let's look at let's look at the equilibrium properties. So this is the grid we're looking at. Detrended capital and firm-specific productivity. You see that the left panel is in the disaster state, the right panel is in the mean normal state, right? On aggregate productivity growth. So you see that that on both panels, only a portion of the state space is plotted, because all the empty, not the number in MATLAB, so that the empty space is when firms exit the economy. You can see that firms exit when they are less productive and relatively big with more capital, because in the model we have fixed cost of production is F times K. So basically in this case, if a firm has bigger capital, you need to pay more costs to remain in production. It turns out those firms at one point, shareholders are going to say, forget about it. So we want out. Okay, so bigger firms and less productive firms are going to exit, right? So on the other hand, this is true beta. The left-hand panel in the disaster, you see those firms relatively small At the same time, unproductive firms, those are later on, those are turned out to be small value firms. Okay, they are most risky. Okay, you see spikes right here, right before the exit. Those firms are actually the riskier firms. So value is riskier than growth in disaster state, in bad times. On this slide, so we're forming portfolios on book to market. Okay, so we are looking at what exactly defines value versus growth firms. Okay, it turns out the left panel is capital, detrended capital. The right panel is firm-specific productivity. It turns out the value firms have more capital than growth firms. The blue line is with disasters. Red line is without disasters. Okay, the firm-specific. At the same time, value firms are less profitable, less productive than growth firms, although the relation is a little bit nonlinear towards the growth end. Okay, so in this case, there's a little bit of a hump shape, but overall, value firms are less productive than growth firms, and the value firms are bigger than growth firms. So in this case, value firms are big firms. Value firms are stuck with a lot of unproductive capital. So I over K is investment rate. You see growth firms invest much more than value firms. So the right panel is true beta. With disasters, you see the turbocharged asymmetry mechanism. Value is riskier than growth, especially in bad times. In our model, we have a disaster state. It blows up value versus growth risk big time in disasters. So this is the value, this is the growth. You see towards the value, and you see the risk relation is convex. Whereas without disasters, it rises up only a little bit. That's virtually flat. The relation between risk and the book to market is virtually flat in normal times, whereas in the disaster state, you see it spikes up. So these are the theoretical properties of the model in competitive equilibrium. Now let's look at the quantitative results on the CAPM. So book to market deciles. So on average, we explain the value premium. Okay, the t-value is a bit too high relative to that in the data. The reason is that in the model, exogenous disaster model, it's pretty well known from Jessica Wachter's influential work, 2013 at Journal Finance, that exogenous disasters model, you don't get a whole lot of volatility. In a production economy, is even more so. All right, so we do not have a whole lot of volatility, and that's why standard errors are small, t-values go up. These are the no disaster sample. I should explain. So we simulate, I'm relying on my memory now. I'm gonna go with 2000. I believe it's 2000 samples. And within the 2000 samples, we say whenever there's at least one disaster in a given sample, we call that sample a disaster sample. Otherwise, it's a no disaster sample. So this table is the averaged across no disaster samples. Okay, so we see we have value premium 40 basis points. CAPM alpha is 25 basis points per month and significant. In this sense, we failed the CAPM. We explained the failure of the CAPM in explaining the value premium. This is a weakness of the Zhang 2005 model, but it's not the weakness, and this model fixes that, explains that anomaly, that fixes that problem. So beta is not small, it's positive, but it's not that big. So 0.18, it's within a reasonable range vis-a-vis the, let's just say the previous post-compustat evidence on beta lies within the confidence interval from the model. And it's not that far on top of that. I think it's 0.07 if I remember correctly. Is not that different from the model estimate 0.18. And the beta is insignificant. Whereas if you average across disaster sample, okay, whenever this is the sample, whenever there's at least one disaster in a sample, we call that artificial sample disaster sample. It's the value premium is a little bit higher, okay? So we are overfitting a little bit in the sense that our beta is too big, is 1, and the CAPM alpha is even negative and significant, okay? So we're overfitting a little bit in this regard, but we do explain the failure of the CAPM in the post-compustat sample. So nonlinearity in the CAPM regression. So remember the figure I reported very early on, that the extreme 3% extreme observations, right? With the extreme observations in the data, you see the beta, CAPM beta showing up for value premium. Without extreme observations, as in the post-compustat data set period, you get slightly positive, largely flat. We replicate that pattern in the simulation. I should mention this is a disaster and death recoveries. We only have 5 normal states. That's why you see 3, basically 3. This is basically one block. Disaster, normal times, and recovery, 3 large blocks in simulations. If we want to save computational costs, the model it's already pretty difficult to solve. If we use enough grid points for normal times, we simulate the model long enough, and then all these scatter plots are going to be connected. But we have to make the model feasible computationally somehow, and that's where we save the computational costs. So bottom line is that it won't change the key moments that we emphasize in the model. So this is nonlinearity in the CAPM regression. Now let's look at the nonlinearity in the pricing kernel. The pricing kernel is very nonlinear. So that's the disaster state. This is the recursive utility pricing kernel. Now we are reporting a scatter plot of pricing kernel against the market factor. That's the disaster states in which pricing marginal utility goes through the roof. That's where the pricing kernel is. This is the recovery states where marginal utility is extremely low. Those are the normal times. So if you fit the CAPM regression, the CAPM will capture something, okay, but not nearly enough to capture the nonlinearity, right? So I will come back to this point later. This is important. CAPM captures some of the impact of the pricing kernel, but not the whole lot. Whereas without the disasters and the related recoveries, CAPM will, not even close to capture the true pricing kernel. We only see one portion of the data, finite samples without disasters. That's when CAPM will fail. And this is the intuition. This is the causal mechanism behind the disaster. This is the intuition behind the disaster mechanism for explaining the failure of the CAPM. Beta anomaly, just briefly, the paper contains more details. We replicate that, and this has largely nothing to do with disasters or not. This is no disasters. You get pretty much tiny, close to zero average return spread. It aligns with the post-ranking beta. As a result, alpha is significant and negative. And that's the point. And with disasters, the results are similar, although alpha becomes only marginally significant, still pretty sizable, 24 basis points, and negative, but the t-value is insignificant, only 1.74. But bottom line is that sorting on beta, even within our model, is basically noise. It's all noise. So again, look at the disasters or not. Look at this figure. It really doesn't capture a whole lot of the pricing kernel. So, and on top of that, if you add in 60-month rolling window, I mean, it really doesn't capture a whole lot. I think, and we calculated the correlations between the rolling beta that we are sorting on with true beta that we can calculate within the model. The time series correlation is only weekly and even weekly negative. Weekly negative in the no disaster sample, weekly positive in the disaster sample. Because disaster, right, with disasters, the disaster state will tilt the CAPM, you know, in the right direction. So so there's a little bit more economic force, disaster force going on. So it drives a weekly positive correlations, but still quite a bit of long ways to go with a linear model. All right, now let's look at the arguably most important part of the paper, which is the consumption CAPM. So I'm not aware of other studies that looked at the performance of the consumption CAPM in a production economy, and mostly because general equilibrium production economies that literally bite the bullet to solve Croissant-Smith are rare. And only after you do that can you talk about the consumption CAPM performance, and this is what we have. We're replicating, this is Jagannathan Wang setting, although I should say we cannot explain the Jagannathan Wang fourth quarter consumption growth success, because in the model, fourth quarter and first quarter, for that matter, second, third quarter, don't make any difference, right? But we do explain the failure of the consumption CAPM more generally. So this is 25 size and booked market portfolios. This is the disaster model, disaster sample in the model. We do explain right. So we do explain value premium being bigger in small firms than big firms. Okay. So value premium in small firms, we're looking at almost 10% per year. In the big firms, big stock quintile is a little bit over 2%, 2.2% or so, a little bit less than 2.2%. So the model explains the fact that value premium is stronger in small firms than in big firms. This has nothing to do with Schleifer vision in 97. This is purely based on production side decreasing return to scale. Okay, because of decreasing return to scale, remember the big positive spikes, the figure on the state space I showed you earlier. So big positive spikes in true betas, that happens mostly among small firms and the low productive firms, small value firms. Okay, big firms, they're actually less risky. And big firms with bigger capital, detrended capital. So that's what we have. And so we do explain that, and there's nothing to do with the limits to arbitrage. I'm not saying limits to arbitrage are not important. So all I'm saying is that from the firm side, that we generate we're generating similar predictions. In terms of consumption beta, they're all negative and go the wrong way. Again, small value has lower consumption beta than small growth. quarterly data on no disaster sample is similar. In a sense, slightly better, because now small value actually has a little bit better, higher consumption beta than small growth. That goes in the right direction. Let's look at the test. This is a second stage cross-sectional regressions using 25 size and book to market as the testing assets. Again, the model is rejected. The linear consumption, contemporaneous consumption CAPM is rejected. The model can explain the failure of the standard consumption CAPM, and that's an important result. Okay, so I'm actually not aware of other prior studies that have talked about this. So it's rejected. That's basically, and if you look at, that's the null hypothesis again is phi zero intercept plus residual being zero, add up to zero, and the model doesn't hold. Individual slope, individual intercept is significant, ought to be zero, but it's not. And the price of risk is even negative. And the results are similar in the quarterly sample without disasters. So the failure of the consumption CAPM doesn't matter with or without disasters. Now, so then we looked at, it must be the consumption growth and the true pricing kernel are not that related. Okay, and that's indeed the case. So we replicate all this consumption CAPM tests, but instead of consumption growth, we use the true pricing kernel. And this is what we have. True price, the true betas are indeed a bit higher for value firms, are indeed higher for value firms than growth firms. And the t values as well. T values are significant. For quarterly sample, true betas, actually, these are not true beta. These are linear regression estimates, unconditional estimates of the true betas. So this again go the right way, 0.25 for small value, 0.12 for small growth. Okay, they go the right way, which is good. And you run the second stage cross-sectional regressions. Now we're doing way better. The model is not rejected. In other words, the linearized version of the truly nonlinear model is not rejected. All right, so the p-value is 55, with disasters 51.51, without disasters, the intercepts are close to zero, the slopes, the price of risk are significantly positive. But we see that even the linearized model, even using the true pricing kernel, the model performance is not perfect in the sense that actually the intercept is significant, although the magnitude is small. Although the Shanken adjusted t-value is not significant, but without disasters, it is significant. Okay, so the performance is not perfect on top of that. 51, 55, you know, it's not small, but it's not 100%. Oh, sorry, I didn't mean that. So I mean it's p-value. Sorry, I meant R square. So with R square, with disasters, is 89. That's pretty impressive. But without disasters, R square falls to 43. So the performance is not perfect. All right. So because the true model is really nonlinear, but we're feeding a linearized model, and especially in finite sample without disasters, and that's when you see the R square is going to fall. All right. So this figure is shocking. Okay, so this is the scatter is very surprising on first glance, but then later on, then when we started to dig and double check, triple check our codes to make sure we have no mistake, and then okay, let me explain. We're reporting scatter plot of pricing kernel against contemporaneous consumption growth. If contemporaneous consumption growth is a good proxy for the pricing kernel, we ought to see something like a 45-degree line lining up. The result is far, 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 far away from that. If anything, the red pluses, these are actually disasters. You don't see any gigantic movement, obvious movement with contemporaneous consumption growth. If anything, the correlation between the true pricing kernel and the contemporaneous consumption growth is virtually zero. It's weakly negative. Weakly negative without disasters, weakly positive with disasters. So actually, I'm relying on my memory now, which is unreliable. You should read the paper. The specific estimates are reported in the paper. Bottom line is that they are not that correlated. Positive or negative, I may be flipping disaster versus non-disaster. But bottom line is that correlation between true pricing kernel and consumption growth is fairly weak. If anything, is weird in the sense that if you look at the disaster states are not associated with the immediate consumption growth drop. Keep in mind, this is monthly observation, contemporaneous monthly. All right. On top of that, the green scatter points, these are recoveries. Recoveries are actually associated with low consumption growth. And Hang and I, when Hang first generated when Hang first generated the result, it was like, it took him, the scatter plot took him 5-10 minutes to calculate, to report, but took him 3 hours. And I couldn't wait. I called him up. I was like, Hang, what's going on? What took you so long just to plot the scatter plot? He said, the results are so weird. I'm worried about making a mistake. It was like after 3 hours, I was like, send the results to me and let's think together. So we stare at the computer screen and we double check the MATLAB codes and we couldn't find any mistakes. And then later on, we read Francois Goriot's AER paper. Again, we read his paper multiple times, but at that time we read his paper again, and then we realized this is actually correct. It makes total sense. It turns out at the onset of disaster, pricing kernel is forward-looking. It reacts right away. Just like remember that early on, I plotted the pricing kernel against the market factor. Market is forward-looking as well. That's why the CAPM factor actually captures some of the impact of the pricing kernel. But consumption growth is totally different because the investor is anticipating multiple years of extreme bad times. Marginal utility goes way up. Investment is going to tank right away. The investment is forward-looking. The investment is going to drop right away. And because of the substitution effect, in that month, consumption in the model actually goes up. Okay, that's the counterintuitive part. In the first month, investment will drop so much, consumption actually goes up slightly. And only after the first quarter in the model, first year, consumption starts to drop. And that's the powerful consumption smoothing mechanism that effectively eliminates any contemporaneous correlation between consumption growth and the pricing kernel. And similarly, analogously for the recovery states. On the onset of recovery, the investor is so happy, marginal utility drops way down. Investment is gonna jump up right away. So much so, consumption actually drops contemporaneously. because substitution effect is so strong. Okay, and that's why contemporaneous consumption growth in the recovery state is actually pretty large and negative. And this is really bad news, in my view, for the consumption CAPM as an empirical model. In my other writings, I criticized the consumption CAPM on the basis of consumption. Oh, sorry, on the basis of aggregation. Well, is this representative investor, right? Who's the marginal investor? What does a representative investor represent? Right? But in this model, we are actually working with a representative investor. But because the disaster model is so nonlinear, the linearized consumption, the standard consumption CAPM really doesn't do much. If anything, it goes the wrong way. So this is, well, I depart from some of the, more influential writings, and I've been following Cochrane my whole intellectual career. So I credit Zhang as the father of investment-based asset pricing. But on this score, partial versus general equilibrium, so I'm departing quite a bit. I'm departing. So basically, this is in one of his review articles early on. So bringing multiple firms, fine, right? This is what I was doing in my thesis, right? He talks about the importance of cross-sectional distribution. Don't downplay the contribution, making Croissant-Smith algorithm to work. It's non-trivial in a model with risk. So then he goes on and say, many of the above papers circumvent this problem by modeling discount factor directly as a function of shocks, meaning we are working with the exogenous pricing kernel. So although the idea, the philosophy, not philosophy, the modeling choice is that by specify a pricing kernel exogenously, we take the equity premium as given. We do not explain the equity premium puzzle, but given the equity premium, and we can say a lot endogenously about the cross-section of risk premiums. And that's what the contribution is. And then he goes on and says it's a fine shortcut, but in the end, we don't really understand the risk premium until they come from basically general equilibrium fed through a utility function. So, that's where we make our departure somewhat. In particular, in our first draft, dated 2015, we didn't do the general equilibrium. If you dig out, this must be somewhere on the internet. So if you dig out that draft, look at the partial equilibrium results. The results are, it's a different calibration, of course. The disaster size and probability are a bit different, but the mechanism is quantitatively similar. We still explain the failure of the CAPM. And of course, we cannot say anything about the failure of the consumption CAPM, right? And I do agree that some allocation of labor, recently reading up on philosophy of sciences again, philosophy of science literature, Philip Kitcher would say, what's the optimal allocation of research time across different topics, right? I do agree some, general equilibrium production economy with heterogeneous firms deserves our attention, that once in a while we should work out such a model, but I argue for a more pluralistic perspective on general equilibrium. It depends on our questions, right? It depends on our questions. We do learn quite a bit from partial equilibrium models, like the Farmer French three-factor model. We do learn a ton from that model, and highly effective. All right, so now let me let me talk about the comparative statics, not in great details, but just summary. Increasing disaster size and persistence raise the value premium, and basically enhance the nonlinearity and exacerbates the CAPM failure in non-disaster sample. Quite intuitive. Raising disaster probability goes in the same direction, but its impact is small. This may be counterintuitive, but it's actually not. The reason is that disaster probability turns out only determine how many times, what's the fraction of disaster sample you're going to see out of your total number of simulations. But all our moments reported are conditional on a disaster sample, right? So once you have a disaster sample, a disaster probability doesn't really matter. Disaster size matters and the persistence, and that's the intuition. Recovery size and persistence have virtually no impact on the value premium or the CAPM alpha. The reason is that value premium is mostly about the downside, bad time, risk in the bad time, right? Because our utility function is concave, marginal utility in good times is small, and the value premium is driven by disaster risk with high marginal utility. So it turns out recovery size and persistence have virtually little impact on the value premium. That's why I said early on, these two parameters, I should be very clear. These are a little bit of like our free parameters. We can adjust to make sure we have the right disaster probability, disaster size and persistence to explain the CAPM failure, but at the same time, we can match whatever the macro history panel by adjusting the recovery size and persistent parameters. And I just want to make it very clear. So fixed cost raise the value premium, you know, this is pretty well known in the investment literature, but it decreases CAPM alpha because higher risk cost generates more operating leverage, and that increases beta and CAPM beta, and then of course CAPM alpha is going to go down, relatively speaking. So even though average return goes up as well. So liquidation value reduces the value premium. If you let the shareholders get more out of the firm in bankruptcy, you are giving shareholders an abandonment option for free. And of course, in that case, shareholders are not going to be stuck holding the bag of unproductive capital. So the costly asymmetry, costly reversibility causal mechanism is going to have less force, less bite. Okay, and then in that case, value premium is going to go down, and the nonlinearity is going to go down as well. Reorganization, delisting returns have little impact because not a whole lot of firms are exiting the economy. And finally, increasing risk aversion and the EIS strengthens the nonlinear dynamics because both increase the risk premium overall. All right. Let me conclude. So in this paper, we show that the general equilibrium heterogeneous firms economy with disasters is able to explain the failure of the CAPM and the consumption CAPM by inducing strong nonlinearity in the pricing kernel. Okay, so in particular, we explained the failure of the consumption CAPM with the GE production economy with heterogeneous firms. This requires us to overcome the approximate aggregation challenge. So I'm going to end up defending the consumption CAPM. Okay, so I argue that. So in particular, we argue in the paper that the widely documented consumption CAPM failures may have more to do with deficiency of data and test designs rather than the underlying economic theory. So the failure of the consumption CAPM has become a status fact for economic theory to explain. We do not reject the underlying economic theory. We only reject a certain functional forms empirical specifications of the consumption CAPM. However, more generally, I've argued elsewhere, because we don't know who the marginal investor is, right? If the marginal investor's pricing kernel is like Epson Zing recursive utility facing some disaster risk, that pricing kernel is going to be highly nonlinear. So I think it's reasonable for one to ask whether empirically, we should still hang our heads on the demand-based asset pricing model, not just consumption CAPM, including in financial intermediary asset-based CAPM as well, right? So if you look at the investment side, we know who the marginal supplier of risky shares are for Apple Computer shares, such as Apple Computer. And the first order condition for the firm, the investment Euler equation, will provide the pricing equation for all the cross section of returns. So again, I understand where people have been arguing about these things. So more generally, I've started to dig into history of economic thought. People have been arguing about these things for hundreds of years, literally. So this was the marginal revolutionaries against back then the classical economists. The marginalists were the ones that talked about the marginal utility, the buy side. The classical economists, David Ricardo, John Stuart Mill, and even Adam Smith, they were talking about cost of production determination of value. The classical economists are the original investment-based asset pricers. Right, in time, I will have more to talk about that issue. All right, for now, this is all I have for this paper. Thank you very much for your attention. I'll see you in the next presentation.